All right, so we talked about polar graphs. We talked about that there are 4 different types of polar graphs. There are limnosons, there are roses, there are limnoscates, and circles, right? So we identify it by the type of equation. The limnoson is an A plus or minus B cosine or sine theta. So there's something being added or subtracted from that separate from the actual trig function. And if that's the case, then it's a limnoson. And then we said the relationship between A and B tells us what kind of limnoson. So I told you yesterday that I would try to visualize it in your head. If you start with the loop at the left and you use the number line as your guide, the smaller the number, so the negative, that's where the loop comes into play. As you move right on your number line, it would hit +1. That's the next type, and what happens to that inner loop is it's getting pushed out. So while your number line, you're moving to the right, the inner loop is getting pushed in the opposite direction, if you kind of picture it that way. So if it's a 1, it's a cardioid, which is the heart shape. If it's in between 1 and 2, then it's the dimpled limnoson, which has that kind of curve. And then if it is greater than or equal to 2, it's convex, where it has that like flat side. Dominic.
So if it's plus or minus with the A and the B sine and B cosine, that automatically means it's a limnoson?
If it's a number added to it,
then it's a
limnoson.
But if it's, is there another type of graph that has like an addition thing? Like an A plus or minus?
That outside of what
Like,
we're doing, it's possible. Yeah, but
That
not
is,
from
like,
what we're...
Can you get a rose that's like A, like that has plus or minus in the equation?
No.
Okay.
No. Not from what we're doing. We're not doing ships or anything like that. Okay, so then we have a rose, right? And a rose has a number in between the trig function and the theta, but the r is not squared. So if the r was squared, that's a different kind, right? So this is r to the first, and then there's a number in between, and we said in that case, if the number was even, it tells us how many petals, right? But we have to do what to that number? We double it. So we double it if it's even for the number of petals. And if it was odd, we'd keep it the way that it is. So if I was to look at this, A would have been, the first one would be a rose with 4 petals. The second one would be a rose with 3 petals. And then the rose looked, you know, if it had 4 petals, it could look something like this. If it had 3 petals, it could look something like this or something like this. Okay, all of those would be roses. Yep. The A is how far out the petal goes. So I'm glad you said that, actually. So if this was a 2, that means from this distance to this distance would be 2. If this was a 4, it would mean from here to here is the 4. The furthest point out would be the number on the front, which is the A.
And does the sine or the cosine determine the tilt of it?
Yeah,
like
that's going to be your symmetry, which I'll wrap up at the end. Then we talked about circles and limnoscates. So the circles are the ones that don't have anything added or subtracted onto the front of the cosine or the after even, and nothing in between. This is the simplest form of the equation. If it's the cosine, then it's symmetric to the polar axis, which we're going to talk about in a second. All right, and then the last one is your limnoscate. So your limnoscate's that one that's like that infinity symbol, and the limnoscate hopefully is the easiest to identify because it has an r squared, right? That's the only one that has the r squared. And the limnoscate, the other difference is that the A, which is on the front of it, so where the A is the diameter for a circle, the A on the limnoscate, you would square root the number that's there to get the A. So that if that said like 25 sine of 2 theta, the 25 would be square rooted. That 5 is how far out it goes. All right, so that's the 4 different types. And then we talked about how to test to see if it's symmetric. So when we're testing for symmetry, if we're not using the shortcut, which only works some of the time, but if we're not using the shortcut, then we're changing what's in this list in a moment, I'll tell you, and seeing if we get back to the original equation or its exact opposite. So everything would be the opposite sign. So if we're testing for the pi over 2 line, which would mean that something is symmetric along the y-axis, meaning I can fold it like a hot dog, like left to right, and it would overlap, then what we're changing is if we had started with r theta, then we're changing both the r and the theta. So for the pi over 2, it's both that you'd be changing. The polar axis would be if it's symmetric to what used to be the x-axis or the horizontal axis. And for that one, we just change the theta. And then for the pole, this,
like plug in and see if they're the same.
And see if it simplifies. So think about like, remember we talked about yesterday, like cosine is even, right? So that if I say cosine of theta or cosine of negative theta, they both give me the same answer. So they both go back to cosine of positive theta. So if your equation has a cosine in it, that negative on the theta is gonna go away, right? But if it's an r squared and a cosine, both a negative theta and a negative r are gonna go away, which is why it'd be symmetric to both the polar axis and the pi over 2. So it can be symmetric to more than one. The last one's the pole, and the pole is like symmetric to that y equals x line, or if you could fold it down and left in your mind. And for this one, we take r theta and we replace the r with a negative. So anything where r is squared is where that where it would be symmetric to the pole. And then we said that there's two short tests. So the quick test, which only works if it's an r equals sine or cosine. It does not work if it's r squared. But if it is an r equals, then if it's sine, we'd say it's symmetric to the pi over 2 line, because that's my y-axis and sine is y. And if it's cosine, we say it's symmetric to the polar axis, because remember, cosine is our x and the polar axis is our x-axis. So those were the quick tests, just to know from looking at it. Again, r has to be raised to the first power. You can't use r to the second to do that. Okay, so having said all that, let's work through this warm-up. So this one says, sketch the graph of the polar equation r equals 6 sine 3 theta. Looking at it, you could tell me what kind of graph is this? This is a rose, right? A flower. I think I would take flower. That's okay. How many petals does it have? 3 petals. And is there symmetry?
Yeah.
Can I use the quick test? Yes. It would be symmetric to what?
The y.
Good. So you're going to give it to me as pi over 2. It is the y. It is formerly the y-axis, but it has a new name. Okay. Yeah. The sine. So r is raised to the first power, which means I can do the quick test, and sine is used.
As long as there's sine.
Yep. Because if I change theta, it's wrong, right? I get a negative angle. Okay, so now I know if it's symmetric to the pi over 2 that I can enter in points from this side and it would immediately reflect over the left-hand side. So I'm just going to pick some points on that right side to plot a point. I know if it's a rose and it has 3 petals, that it's either going to, and it's symmetric to the pi over 2, it's either going to look like this or it's going to look like this. That's the only way for it to be 3 petals and symmetric, right? So I got to figure out which ones those are. What's an easy way to figure those out? What's the difference between that one and this one? How about the points? Like which one? So one would have my furthest point out at it looks like pi over 6. That's one way to look at it. Yeah. What's the quickest way to find a point? Try 0 and pi, right? Try 0, pi over 2, try pi. If it's the blue one, then if I plug in pi over 2, what do I expect to happen? I should get specifically what letter, what number? 6. If it's the green one, what should happen at pi over 2? I should get negative 6. Does everybody understand that?
No.
So if it's the blue one, let's just say, right? And I plug in pi over 2, then I expect to get 6. That would tell me 6 is the A, and on a petal, that's the furthest out it goes. Does that make sense? Yes. If it was the green one, and I plug in pi over 2, I either expect to get 0 or I expect to get 6. I'm negative 6, sorry, because it would bring me in the opposite direction. That's how, right there, immediately you could differentiate between the two. If you have no idea, you're going to plug in some additional points. So we're going to do that too. But that gives me an inclination of what it should look like. So I'm going to plug in some additional points just to be careful, because you're not always going to understand what you're looking at. So let's say I'm going to plug in 0. I'm definitely going to plug in pi over 2. Let's say I pick something from the first quadrant. I pick pi over 4. And then let's say I pick something from the second quadrant. I pick 3 pi over 4. Because I know that what's going to happen on the other side is it's going to reflect, right? Because we said this is a reflected, oh no, wait. Did I do that right? Yeah. It would reflect over the pi over 2. So I don't want to pick those points. I want to pick the ones from the right side. If it's reflected over this axis, then I want to pick points on this side so that I can reflect it over the other ones. So I'm not going to pick 3 pi over 2. I'm going to pick something like 7 pi over 4. All right, so if I plug in 0, 6 sine 3 times 0, 6 times the sine of 0. At 0, sine is 0, 6 times 0 is 0. So I already know this first point. Then I go to the next one. 6 sine pi over 3 times pi over 2. 6 sine of 3 pi over 2. Sine at 3 pi over 2 is -1, -6. And just right there, I know that instead of going up here, I'm going down to 6 on the bottom. And I've already figured out, based on what we talked about before, that I have a pedal that's going down and around here. Which means if this is symmetric to the pi over 2 axis and it's got 3 pedals, my other ones are going here and here. So I want to find at least one point there to figure out how far, where that over 6 happens. I mean, where that 6 is going to go. Where's that furthest point? So if I were to plug in pi over 4, I'm going to skip right to that one, and get 6 sine 3 pi over 4. 6 sine of 3 pi over 4. 3 pi over 4 is over here. My over 4 is root 2 over 2 and root 2 over 2. The sign on that would be positive. The cosine would be negative. So this is a 6 times positive root 2 over 2, which is 3 root 2. And we're going to approximate root 2 to be like 1.2. So this is 3.6.
So you multiply it first, and then you find the point. And you
Yep.
sign of that.
Find the angle. Yeah, and then find that. Yeah. So I know at pi over 4, I'm going out 3.6, which means that that's not my furthest point. Pi over 4, 1, 2, 3.6. Which means I'm either on the return side of that or on the out. Like I'm either going this way or I'm going this way. And to figure out what to do, I'm going to plug in one additional point. So let's say I go with the pi over 3. So 6 sine 3 pi over 3. I'd get 6 sine of pi. The sine at pi is what? Is 0. So this is back to 0, which tells me that it's got to happen at pi over 3. So at pi over 3, I'm back. I'm sorry, it has to happen at pi over 6. At pi over 3, I'm back to 0. At pi over 4, I was, what, 3.123 here, which means it has to come out to 6 here.
Do we have to be that exact?
I would want you to find where the A happens. Yeah.
Well, isn't the A a given, basically, from the equation?
No. You know what A is, but I want you to know where it happens. Like at what angle. And so that I know that if I had picked pi over 6, like you're going to just randomly pick angles. Like you could pick, obviously not randomly, the ones that are on your unit circle. But if you had picked pi over 6 first instead of pi over 3, I would have known that was my 6. And I'd be okay. But because I didn't, because I picked pi over 3, because you're not going to know which one to pick. Because I picked pi over 3 and I was at 0, I know that it had to happen elsewhere. Which means that on this side, the same thing's going to happen. My 6 is at the 5 pi over 6 because this is symmetric.
Are we going to get the unit circle? Like, did you decide?
No. You mean, are you going to get it the day before? Probably.
Oh, we're gonna have it on the test.
Like where you'll be able to fill it out the day
We're
before.
gonna have another quiz.
No.
Yay!
What, we
Thank
still-
you.
I'm going to record that because that was a good question. You need to at least figure out where the A is going to happen. So you need at least one angle of what's going to get you. The one on the bottom, obviously, I had already gotten. I need to know where that shape is going to happen on the top. And this is because it's symmetric to the pi over 2.
So you'll basically need.
So I would duplicate it. Not even, because it's symmetric. So like the one we did yesterday, we only needed one.
So if it's, especially if it's an even number, you can just reflect.
Yeah.
Okay. Cool.
Does that make sense?
Yeah.
Yeah? Okay. I'm going to start you on it. You would distribute the 3 first. Yeah.
Okay.
Either way, it's It's a either way it's a limison, right, from the get-go. But in order to figure out your A and B, you've got to distribute the 3. So it's 3 minus 3 cosine theta. So R equals. So we just said this is a limison. And the A is 3. The A is what you're going to keep the sign on. So if that was a -3, then A is -3. But the B, because we say plus or minus in between there, the B we actually don't keep the sign on. So if you look back at your standard equation, my equations were A plus and minus B, right? So I ignore the sign on the B, but I make sure I did take it off the A. If that A was negative, then it would be a -3 and a positive B. So if it's 3 over 3, then it's 1. And what kind of shape is it if the A over B is 1?
Cardioid.
It's a cardioid, which means it's that heart shape, okay?
And is it facing left because it's -3 cosine?
Facing left meaning your little
like
indentation.
The is here and then the other.
Yep. Yeah.
Negative?
He's just flipping it in his head. So your standard one would be positive, but the negative in
So
front
I'm
would
looking at
flip it back.
Like the graphs on the PowerPoint,
Yeah.
and they're facing the right with the positive, but I asked if it was negative.
But you'll know that as soon as you start plugging in your points. You'll see it. Yeah, yeah. So, and the symmetry, because it's cosine, if I plugged in a negative theta there, it would come back to positive theta. That's your polar axis, right? So this is symmetric to the polar axis. Which means that everything that happens above my x-axis is going to reflect down upon my lower axis. So aside from that, the rest of it you got to figure out, which means you're going to plug in some points. It's not as easy as the pedals. So I'm going to put in some thetas, and I'm going to get out some r's. So I'm going to start with 0. Maybe I'll do pi over 4. I'll do pi over 2. I'll do 3 pi over 4, and maybe even get to pi. So if I plug in 0, I get 3 minus 3 cosine of 0. Cosine of 0 is 1. 3 minus 3 is 0. 3 minus 3 cosine pi over 4, which is 3 minus 3 times root 2 over 2. 3 minus 3 root 2 over 2. I'm going to approximate that. So we said that this is like 1.2. That would be 3 times 1.2 over 2, 3.6 divided by 2, 1.8. So we're saying this is 3 minus 1.8. So I know I did that fast, but I just approximated that value.
You have scientific calculator for this one?
Nope.
No?
Nope.
Just gonna approximate it.
Yep. This would be 1, or sorry, this is 0. 3 minus 0, which is 3. And then I know pi over 3 pi over 4, because we're talking about cosine, the only thing that changes is the sign, the positive or negative sign on this cosine. So this becomes 3 minus 3 plus, or positive, negative, sorry, root 3 over root 2 over 2. So this becomes 3 plus 3 root 2 over 2, and we just said that that's like a 1.8, so we're going to say this is 4.8. And then the last one is pi that I have. 3 minus 3 cosine at pi. Cosine at pi is negative 1. 3 plus 3 is 6. And now I pull out my points. 0, 0. Pi over 4, 1.2. Pi over 2, 3. 1, 2, 3. Oops. 1, 2, 3. 3 pi over 4, 4.8. 1, 2, 3, 4.8. Pi was 6. And then because it's reflexive over that polar axis, I'm going to duplicate all those points on the other side. So pi over 6 here. Pi 1.8 here. 1.2. 10.1 is called the three-dimensional coordinate system. So we're going to, and this is the only section that we're doing from chapter 10. For seniors, this is your last day. Well, we'll probably have to finish that Monday, but this will be your last start to notes. Okay? That should be a happy thing. Yeah. So we're learning how to graph a point and then find information about a point, find the distance between 2 points, find the midpoint between 2 points, and then apply a sphere to this in a three-dimensional coordinate system. The good news is this stuff is super easy, okay? It's hard to visualize it because you're doing a three-dimensional thing on a two-dimension surface, okay? But if you could just use your imagination a little bit, you should be okay in this section. So this says, to identify a point in space, you have to introduce the third dimension to the model. The geometry of this three-dimensional model is actually called solid analytical geometry. So that's where the analytical part of your book comes into play. The good news is this is where you stop, and this is where the analytical class was like about a month ago. Okay, so you can construct a 3D coordinate system by passing an z-axis perpendicular to the x and y axis at the origin. So if you could think about your desk, if you look flat on your desk, and if you could think about drawing a horizontal line and a vertical line straight through your desk, and that's your normal XY plane, right? We're pretty comfortable with a rectangular plane at this point, yes? Now think about taking a pencil or stylus and drawing it directly into where those two meet, so through the origin, vertically. Now you've created a three-dimensional plane. That's what it is. So you've got an axis that's going to run left and right, an axis that's going to run forward and back, and an axis that's going to run up and down. Because it's three-dimensional, it actually can rotate. So you want to pay attention to the letters on your axis. So the one in this picture says that the Z is at the top, so the Z is running up and down. The Y is on the right, so the Y is running right to left. The X is in the front, which is running forward and back. That's pretty typical. I would say that's the most common, but it's not always like that. So you definitely want to look for your X's and your Y's and your Z's. Also in that way, we assume that towards us is positive of the X's, away from us is negative. Right on the Y is positive, left on the Y is negative, and up on the Z is positive, down on the Z is negative. Again, that's standard, but it does switch. So if it does switch, it will indicate it on the axes, okay? So each of these planes are formed by the two axes that actually form it. So if you look at the bottom, or this one that's flat, this is your XY plane that is formed by your X and your Y axes. The one in the back is the YZ plane because it's formed by the Z and the Y. And then on the left there, running forward and back kind of, is the XZ plane because it's formed by the X and the Z. They come from this. So there are 8 octants in this cube. So if you think about a cube, almost like a Rubik's Cube, and you divide it into the 8 quadrants. So you cut it in half horizontally, you cut it in half vertically, and you cut it in half through the last remaining quadrants. You'd end up with 8 little cubes. Each of those cubes is called an octant. So we will typically stick to the positive octant, which is in the front, that first octant, which is in the front, which is the positive system. So if I had just taken that green one, this section here, and I pulled it out, and I looked at it this way, this is just the positive portion of X. So those would be the positive values of X. The negatives would go back the other way. These would be the positive coordinates of Y. And then these, well, here, these would be the positive coordinates of Y. And then these would be the positive coordinates of Z. So if you keep in that first octant, it's all positive. Obviously, we're not going to keep solely in that one. But just think about as it comes forward, it's positive. As it moves to the right, it's positive. And it goes up, it's positive. And then the opposites are the negative values. All right, so if you're looking at this mapped out X, Y, Z axis, it says determine which is the point of 2, -3, 3 in the coordinate plane below. So the first one is your X, the second one is your Y, the third one is your Z. So on the X axis, which is the one that's kind of diagonally coming towards your, like this way, +2 would be forward 2 places. All right, so if it's a +2, it means along this x-axis we're moving 2 places forward. If it's a -3, the y is going like left to right. That means I'm moving 1, 2, 3 places to the left. And if it's up 3, then I'm going up 3 places, and right here is the point we'd be looking at. So this is obviously not going to be like a rectangular shape in which you're moving the tick marks left to right, up and down, because obviously this is a tilted axis, okay? So you're not necessarily, if I'm saying go up to 3, you're not necessarily going up to this 3 straight across the board, okay? The further away you're moving from the axis, it's almost like it's tilted. The lower it's going to look, okay? These are not exact, so don't stress out about it. Just make sure you can get it in the right location and be about the same place you need to be.